Okay, let's get started. Um, Good morning, everyone. Welcome back to today's SNAPP seminar. Today we have Jiaming Xu, who is an assistant professor in the Fuqua School of Business at Duke University. I'm happy to introduce Jiaming because I've known him since our days together as grad students at Illinois. So Jiaming got his PhD degree from Illinois in 2014 under the supervision of Professor Bruce Hayek. He got his master's from Austin in 2011 and bachelor's from Tsinghua University in 2009, all in electrical and computer engineering. He also received a Simons Berkeley Fellowship in 2016. His research interests are very broad and include high-dimensional statistics, information theory, convex and non-convex optimization, and queuing theory. Today, he's going to talk about phase transitions and planted matching problem. So without any further ado, Jiaming, the floor is yours.
Okay. Yeah, thanks a lot for the invitation. I'm very happy to be here. So today I want to present one of my recent work on planted matching problem. In particular, I'm going to tell you actually some very interesting phase transition phenomena that we discovered in this problem. This is actually based on joint work with Jianjing, Yihong Wu, and Dana Yang. I think Dana is also in the audience. I think she will be happy to answer any question that you have in the chat box. And also thanks for everyone for coming to my talk. Like, feel free to interrupt me if you have any questions during the talk. Okay, so yeah, let me actually first talk a little bit about the broad picture of this problem. So the motivation of this work is actually twofold. So here, let's consider from a theoretical perspective, the study of this problem actually motivated by this study of the planted problems. So in many actually machine learning applications, sometimes we encounter the following kind of situation. We have some optimization problem, which actually has some very good solution built in, but somehow that solution is actually obscured by some noise in the problem. So the question now is that how can we actually recover this good solution or the corresponding planted structure from the noisy observation? So here I show you an example of this community detection problem under stochastic block model. And you can see that the communities here actually correspond to this good partition of the network. Like, you have more edges within the community, but you have few edges across different communities, right? But now you can see that there are still some edges crossing different communities. There are still some missing edges within the community. So this makes the good solution or good partition actually difficult to recover. So the goal here for the community detection is still try to find these underlying communities despite this noise. Okay. Another well-known example is actually this plant clique problem in order-Xianyu random graph, where you can imagine you have a large clique, right? And then embedded in an order-Xianyu random graph. And now your goal is to find out the location of this hidden clique. Okay. So in many of these planted problems, we actually see very interesting phase transitions. And also we actually see the so-called statistical and computational gap, in the sense that it may be actually computationally intractable to recover this hidden structure, even though it is informationally possible to do that. So that motivates us to actually consider some planted problems beyond the partition or beyond the clique. Okay, so in particular, we actually in this talk, we're going to consider another kind of structure is actually the graph matching in the bipartite graph. So basically, it's like, imagine you have observed a weighted bipartite graph G here. And now with some hidden perfect matching, M star, say it's uniformly generated at random. Okay, so here I use the red edges here to denote the edges in this hidden matching. But you should imagine the matching can be randomly scrambled. So the edges may not always like these horizontal lines here. Okay, so that's the hidden perfect matching. And now for all the other pairs, like n times n minus 1 pairs that are not in the hidden matching, they're actually connected randomly with an edge independently with probability d over n. Okay, so those generated edges actually are denoted by the blue edges here. Okay, so the average degree for the blue edges is roughly d. Okay, and now for every edge, we also observe the random edge weight, where the edge weight is independently drawn according to distribution p for all the edges inside this hidden matching. Okay. And then for all the other edges not in the hidden matching, the edge weight is drawn from another distribution Q. Okay, so basically the blue edge is drawn according to Q, the red edge is drawn, like red edge weight is drawn according to distribution P. Okay. So now the problem we're interested in is actually, say how you can recover this hidden matching M star by just observing the edge connections and also the edge weight. Okay, in particular, you can see that here you do not see the edge colors. Okay. So the question is that can you still recover this underlying hidden matching M star? Okay. So this definitely depends on how different P versus Q, right? It also depends on how large this edge probability deal ran here. Okay. But before talking about this problem, I want to actually mention a very interesting relation to this celebrated random assignment problem. So basically, if you imagine D equals N, and then P and Q are just both exponential distribution with rate 1. Okay, in other words, you have this complete bipartite graph where every edge has weight drawn from exponential distribution with mean 1. Then this actually reduced to the random assignment problem. There, the question is not to look for this hidden matching, but instead try to find out what's the expected value of the total weight of this minimum weight matching. Okay. So this problem actually inspired lots of very famous probabilists to work on. And then this actually has very interesting history. So back in the 80s, actually Mézard and Parisi actually first conjecture the limit for this expected value is actually pi squared over 6. I mean, this is the zeta 2 limit. This conjecture was later proved by Aldous in 2001. And now, in fact, in this exponential model, actually now Prabhakar and Sharma, so they actually proved that for finite n model, the exact value is given by the first n terms of the zeta 2 series. Okay. So the result here is actually very interesting and amazing. But in this talk, I'm not going to particularly talk about this random assignment problem. Instead, my interest is actually to recover this hidden matching from the observation where P and Q may be different. Okay. So the study of this Planté matching problem actually also has a very practical kind of implication. So in particular, this is inspired by this problem called particle tracking. Okay. So imagine like in many applications, you may encounter some different like moving objects. So now you may be interested in kind of tracking their moving trajectories, right? So basically it's like these subjects can be actually flocks of birds or swimming microbes, right? And now you want to actually basically, here I focus on like two kind of video frames. You can imagine you have a sequence of video frames. If you focus on two video frames, you want to match the object in one frame to the correct correspondence in the next frame, okay? And then if you can match them correctly for every 2 consecutive frames, then over the course of the video, you can track the moving trajectories, right? So here is actually a graph illustration of this process for tracking particles. So on the left-hand side, actually, the plot is actually superimposed, like 2 frames superimposed on each other. So the red dots here represent the particles in one frame, and now the blue dots actually represent the particles in the next frame, okay? And then you can see that from this left plot, you do not see the underlying matches between the red particles and then the blue particles. On the right-hand side, I actually show you the true matches and also their corresponding movement, okay? So basically the particle tracking problem is try to go from the left plot and try to infer the right plot, okay? Try to actually recover the correct one-to-one mapping between the particles in one frame to the particles in the next frame, okay? And this problem actually can be modeled as this Planté matching problem because you can imagine actually the left and right vertices corresponds to the particles in these 2 frames. And now this hidden perfect matching actually corresponds to the true one-to-one correspondence between the particles in one frame to the particles in the next frame. And now the edge weight, the observation of the edge weight actually can be viewed as the pairwise distance between the positions of these particles. And now you can imagine that probably statistically you would expect the true matches will have a relatively small pairwise distance than actually the fake matches, right? But then still you may actually have some true match will have a long, like a very large pairwise distance. You may also have some fake match that have very short distance. But then you still, your goal is still try to figure out what's the underlying matches despite this noise in the problem, okay? So that's the motivation, another motivation of study this Ponte matching problem. Okay, so now back to the problem. If we want to solve this Ponte matching problem, a very kind of natural attempt is to do this maximum likelihood estimation. And basically in this problem, it actually reduced to this following maximum weighted matching problem, where we basically want to search over all the possible perfect matchings that maximize the total log likelihood weights of the observed edge weight. Okay. And now since we're looking at a bipartite graph, this actually can be computed in polynomial time as a linear assignment. Okay, so there's no computational issue here. But now here, the crucial thing is that, I mean, even though you believe the true matching M star, right, will have a high likelihood, but it may not actually be the maximum likelihood, right? So the question now is that how much does the maximum likelihood estimator have in common with M star? Okay, so in particular in this talk, we're going to focus on this measure called reconstruction error. So that is actually the expected value of the cardinality of the set difference between the maximum likelihood estimator and M star, and then normalized by the total number of edges in the matching, that is M. Okay, so basically this captures how different M hat compare to actually the true matching M star. Okay, and then also another question is that this maximum likelihood estimator may not be optimal in minimizing this error. Okay. So now the question is that, okay, what is the information theoretical limit of this reconstruction error? Okay, what's the best you can do in this case? Okay, so the main focus of this talk is trying to answer these two questions. Okay, now here is actually our first main result. So basically we identify a sharp phase transition threshold in this problem. And the threshold is actually determined by this so-called Barachari coefficient. Okay. So this Barachari coefficient basically measures the similarity between distribution P and then Q. Remember, P and Q are the distribution for the edge weight. Okay. So if P and Q are the same, for example, then the Barachari coefficient is equal to 1, right? Because here it just becomes integral of the distribution, so you get 1. On the other hand, if P and Q are completely kind of mutually singular, then the Barachari coefficient will actually become 0. So here's our main result. Basically, we show that if the square root of the average degree, so D is actually the average degree for the blue edges. So square root of average degree times this Barachari coefficient is less or equal than 1, then actually the reconstruction error for the maximum likelihood estimation actually converging to 0 as n goes to infinity. Okay, so in other words, this maximum likelihood estimator is actually like a coincide with M star, like almost perfectly. But then on the other hand, if we further assume like this model parameter dpq are independent of n, then actually if the square root of average degree times the Barachari coefficient bigger or equal than 1 plus epsilon, then actually for any estimator, the reconstruction error is actually lower bounded by some positive constant. Okay. So in other words, this shows that actually in terms of whether you have vanishing reconstruction error, the sharp threshold is given by square root of d times b pp, like the Barachari coefficient equal to 1. And also I should mention that epsilon here can be arbitrary small constant. So this in particular resolve actually the previous conjecture in the previous work. And also I want to point out that here, you know that in this converse result, I assume this D actually is a fixed constant independent of n. But the same result can be generalized to actually the dense model as well, where D actually can grow with infinity as n grows. Okay, but here the distribution Q need to actually do some proper scaling. So let me give you a more precise example in this dense model. So for example, D equals M. So in other words, you have a complete bipartite graph. And now P is actually exponential with rate lambda, and then Q is exponential with rate 1 over n. Okay, so here, if you talk about the mean is actually 1 over lambda versus n. Okay, so in this case, this Barachari coefficient like threshold can be just reduced to lambda equals 4. Okay, so when lambda is bigger than 4, then actually you know the maximum likelihood estimator will actually coincide with M star almost perfectly. When lambda is less than 4, then actually is the reconstruction error is always lower bounded by some constant. So this in particular resolved the conjecture in the previous work, which studied this exponential model. Okay, so this is our first result, but I want to point out that here the answer is not that complete in the sense that the reconstruction error here, we do not give a very explicit bound on the reconstruction error, other than say it's lower bounded by some constant, right? So it turns out that actually we can get a more precise result about the reconstruction error in this exponential model. So here's actually what we're going to consider next. So if you look at the exponential model, remember lambda equals 4 is the threshold. And if you slightly below the threshold, lambda equals 4 minus epsilon, where epsilon is a small constant, then actually we can show that the reconstruction error for maximum likelihood estimator is actually roughly exponential raised to the power of minus 2 pi over square root of epsilon. Okay. But then on the other hand, we also can show that for any estimator, the reconstruction error is actually lower bounded by exponential minus some constant divided by square root of epsilon. Okay, so these two results together basically show that the optimal reconstruction error under this exponential model is actually exponential with rate minus 1 over square root of epsilon up to some constant factor. Okay, and in particular, you can see that this expression here as a function of epsilon is actually infinity order smooth. Okay, so in other words, if you take this divide by any power of epsilon and let epsilon goes to 0, this will go to 0. Okay. So this is actually known in the statistical physics parlance. This is actually known as so-called infinity order phase transition. Okay. So one thing that I want to point out that this infinite order phase transition is actually quite unique. So in many other quantitative problems, we actually only see finite order phase transitions. So for example, like in this stochastic Rock model, in this community detection problem, if you have two groups, we see this second order phase transition. Second order here just means that the reconstruction error is actually continuous, but its derivative is actually discontinuous. And then if you have more like at least 4 groups, then the phase transition is actually first order in the sense that the reconstruction error itself is actually discontinuous. So you have a jump. Okay, but in this exponential model, it turns out that the order is actually infinite. So in particular, to get this result, our upper bound here actually follows from analyzing the maximum likelihood estimator. So in particular, the previous work actually determined the exact reconstruction error of maximum likelihood estimator. So here, here, instead of looking at error, here I'm looking at the overlap. So overlap is just 1 minus the reconstruction error, roughly. So in this previous work, they can derive this exact overlap as in terms of the solutions of the ODEs. And you can see that this overlap indeed converges to 1 as lambda goes to 4. Or in other words, the reconstruction error goes to 0, right? So you can see here, through these numerical results, it seems like the threshold here, is actually indeed infinity order smooth. So our result basically confirmed this. This is indeed the case. And also our upper bound of this reconstruction error is actually follows from analyzing these ODE solutions. Okay. But here, this ODE is actually a system of 4 like variables. So I'm not going to actually talk in more detail about this ODE solution here. I think that's all I want to say about the results. But I want to actually pause a little bit and then give some opportunity to ask any question that you have, like try to answer any question that you have in terms of results.
I wanted to ask why this particular measure of distance between probability distributions comes in. Will you be speaking about that later on?
Yes, so you will see that immediately when I talk about analysis. This actually pop up in this large deviation analysis of the edge weights. Yeah, so I will talk about that. Any other questions? Okay, so then I will proceed then to the analysis. So let me actually start with the analysis of the positive result. In particular, we are going to consider the maximum likelihood estimation. So the idea is that, remember, we want to show the maximum likelihood estimator is close to the true matching, right? So in other words, it suffices to show that for all the matching that are far away from the true matching, the likelihood is actually lower than the true matching. So we do that in 2 steps. We first actually focus on all the matchings which differ from M star, like true matching in 2 T edges. And we can count how many there are. They're at most n choose T times T factorial, right? Because you have T edges, they are differ. So you can choose n choose T. And then for all these edges differ, you can actually consider random permutation. So you have T factorial. And now for each of these matching, you can compute the probability of this matching actually has a higher likelihood than M star. And this probability should be smaller, right? And this is given by this, the probability of the log likelihood weights of all the edges in M, but not in M star, actually bigger than the log likelihood weights of all the edges in M star, but not in M. And this is given by this large deviation upper bound here. In particular, remember D over N is the edge probability for blue edge to appear. And now this Barachari coefficient actually come from this large deviation analysis of the edge weights. Okay, basically here you have sum of independent log likelihood weights. And now you just need to look for the Chernoff bound, and then you will see the Barachari coefficient popping out. Okay, now with these two steps, now I can just take a union bound by summing over all the matchings and also sum over all the distance t that is bigger or equal than some beta times m. And you can quickly realize that the crucial term here is actually d times the Barachari coefficient square. So remember, our Sharpe threshold is actually square root of d times Barachari coefficient less or equal than 1. Then you can quickly realize the term here actually will go to 0, as long as the beta is actually properly chosen as some vanishing term. Okay. So that basically showed that no m actually has a higher likelihood, no m actually with distance bigger than beta n actually has a higher likelihood than m star. So the maximum likelihood estimator then has to be close to m star. Okay, so that's the positive part of the proof. So this is actually relatively simple, but the more challenging part is actually proving the negative result. So the crucial thing here is that this maximum likelihood estimator may not be optimal for minimizing error anymore. So we cannot just look for focus on maximum likelihood estimation. Instead, we need to actually analyze this entire posterior distribution. Okay, so here is the posterior distribution of the matching given observed weight W. This just it's just proportional to the exponential of the log likelihood weights. Okay, and now here a very simple but crucial observation that we use here is that even though the maximum likelihood estimator is not optimal, but we know if you sampling from the posterior distribution, it's actually optimal within a factor of 2. Okay, so this actually can be proved as a simple exercise. So basically, you can imagine you have m tilde that is drawn from the posterior distribution, and you can consider any other estimator, m hat. Okay, and now here, if you look at the difference between m tilde and the m star, this just by triangles inequality can be upper bounded by the difference between m tilde and m hat and the m hat and m star. Right. Now here, a very crucial thing is that m tilde is drawn from the posterior distribution, right? And then according to the model, m star also follow the posterior distribution when you condition on the weight. So that's why m tilde and m star actually are statistically indistinguishable. Okay, so that's why these two expectations here actually are the same. So that's why you have 2 times the expected value of the difference between m hat and m star. And that's the reconstruction error for m hat. Okay. So now because of this observation, basically if we want to lower bound the reconstruction error, it just suffices to actually focus on the posterior sample. We are losing at most a factor of 2. Okay. So that's exactly what we're going to do next. We're going to analyze this posterior sampling. So to do that, we actually do that in 2 steps. Okay, so the first step is that we try to upper bound the posterior mass of matching that are very close to m star. Okay, in particular, we consider a ball of radius delta m, and we consider this white region, like all the matching that differ from m star by at most delta m edges. And we can actually show that the total probability mass in this white region, normalized by the posterior probability of m star, is actually at most exponential times some constant 7 times epsilon times delta times m. Okay, so that's the first step. And now in the second step, we're actually going to lower bound the posterior mass of the matchings that are far away from m star, like in this gray region. Okay, in particular, we can show that the posterior mass in this gray region, normalized by the posterior probability of m star again, is actually now bigger than exponential 14 times epsilon times delta times m. Okay. So now if you have these 2 results, this immediately implies that the posterior mass in the gray region is actually exponentially larger than the posterior mass in the white region, right? You have much more posterior mass in the gray region. So that's why if you sample from the posterior distribution, then very likely the sample will land in this gray region. and in particular differ from M star by at least the delta n edges. Okay, and then how large the delta that you can do in these two bounds actually determine what's the reconstruction error lower bound that you can have in the end. Okay, so now let me talk a little bit how we prove this upper and lower bound. This upper bound is actually relatively easy. So the intuition here is that you look at those matching that are close to M star, right? So their likelihood actually may be larger than the likelihood of M star, but it cannot be too large because they're close. Okay, and also you do not have many such matchings because you only consider this ball of radius delta n. So that's why if you do a calculation, you can see that this posterior mass can be upper bounded by this factor. But here you still need to do some proper analysis, like some proper conditioning, but it's not that difficult. The main challenge is actually the lower bound here. So the key for this lower bound is actually we try to construct actually exponentially many matchings in this gray region, and actually has a higher or same likelihood than the M star. Okay. So if we can indeed find such exponentially many matchings, then immediately this will imply the lower bound on the posterior mass in the gray region. Okay. So that's what we're going to focus next. But then to do that, actually another simple but useful observation is that if you look at the matching and then compare the difference between the matching M and M star, this can be viewed as the disjoint union of alternating cycles in this bipartite graph. Okay, here's kind of an example to illustrate that. So M star is actually the true matching. It's given by these solid horizontal edges. And the M is actually given by these 3 dash edges here, and also one edge between 4 and 4 prime. And now if you consider the symmetric difference between M and M star, now it just boils down to this actually 6th cycle, okay, as I shown here. And also this cycle actually alternate in color. So the red edge actually represents the edges inside this true matching M star. And then the blue edge represents the edges actually in this matching M. Okay. And you can see that this alternating cycle will always alternate in colors. Okay, now with this alternating cycle representation, then our goal just reduced to actually find exponentially many long alternating cycles, okay, that are so-called augmenting, in the sense that the log likelihood of all the blue edges exceeds the total log likelihood weights of the red edges, okay? And then if they are augmenting, then you know through this alternating cycle, you can construct a matching that has the same or higher likelihood than M star. Okay, so now the remaining job is actually to see how we can find such long augmenting alternating cycles. Okay, so here one idea that you can try is actually to use the so-called first and second moment method. So basically you can define a set S as the set of such augmenting alternating cycle in the graph G of length at least constant times n. And it's not hard to actually to show that on average, you indeed actually have exponentially many such alternating cycles. Okay, but now the crucial thing here is that the actual number of alternating cycle may fluctuate away from the mean, right? But then if you can show the second moment is actually smaller than some constant times the mean square, then you can use this so-called Parisi-Ziegman inequality to quickly conclude that the cardinality of the set S indeed concentrate, at least with some constant probability to the mean. Okay, but then for this problem, unfortunately, this program does not work because fundamentally, actually, the second moment of the cardinality of S is actually much bigger than the mean square. The short explanation is that there's too much excessive correlation among these different long cycles. Because we need to consider linear in n cycles, they actually tend to overlap a lot. So somehow this natural attempt fails. So our resolution here is actually try to not directly search for cycles, but instead do that in 2 steps. So first, we try to find actually many short disjoint passes. And now in the second stage, somehow we are able to connect these passes into long cycles. Okay. So in particular, this idea gives us this so-called 2-stage cycle finding scheme. So let me actually explain the idea here. So basically, imagine now you have like this bipartite graph, right? So you first reserve a set of vertices called V of roughly gamma times n vertices, where this gamma is actually will be chosen as a very small constant here. Okay, so you reserve a very small portion of left vertices and also its corresponding right vertices. And now in the first stage, okay, you're trying to actually find many short, in particular constant length augmenting alternating passes using the non-reserved vertices, like in this V complement. Okay. And now in the second stage, now you're trying to connect these passes into long cycle using the reserved vertices in V. Okay. So let me actually dive in to tell you more about how these two stages really work. So here is actually the first stage. Okay. So to find these alternating short passes, in fact, we actually try to first find like a pair of vertex set called LK and RK. So LK is actually a set of left vertices, and RK is actually a set of right vertices. And we want to make sure every vertex in LK and then every vertex in RK actually are connected by an augmenting alternating pass. So here I use this dashed line actually to denote this augmenting alternating pass. Okay. And I want to actually find many such pairs, like LK and RK. In fact, I want to find roughly linear in N many such pairs. Okay, so that's the first stage. Okay. And now in the second stage, I'm trying to actually connect this LK and RK to form a cycle. So this is called sprinkling. The idea is the following. So we first actually try to actually find the reserved vertices connected to LK and RK. So in particular, let me do slow here. So for L1, for example, are we able to find actually U1 prime, that is the reserved vertices connected to LK, like L1 here? And also I will find the V1 as a set of reserved vertices connected to R1. And then do the same thing for the others. Okay. And then also note that here, because in the end, we want the cycle to be alternating. So this UK and VK naturally induce the corresponding like counterpart, like UK prime will have UK and VK will have VK prime through these red edges. Okay. And now in the second stage, we're actually going to actually look for the blue edges connecting this UK and VK prime. So for example, if we can find a blue edge connecting U1 to V2 prime and a blue edge between V1 prime and U2, then I claim actually combined with my previous stage, I find an alternating cycle. Okay, so let's see how it works. Basically, remember, I have this like augmenting path connecting L1 and R1 and connecting L2 and R2, right? Now, let's say I start from U1, this node. I follow this path, and then through this augmenting path that I found in the first stage, I will actually get to V1 prime. And now through this long blue edge, I will actually arrive at U2. And now again, through this augmenting alternating path I found in the first stage, I return back to V2 prime. And then through this long blue edge, I return back to the original starting vertex in U1. Okay. So you can see that through this procedure, indeed, I find the alternating path. Okay. Here, I want to mention that for illustration, I only consider like k equals 2 here, but you can imagine this can be done for many such pairs. Now, like a useful representation that we can use to simplify is this so-called supergraph, where basically we can imagine like the vertex k here represents this UK, and k prime represents VK prime. And now k and k prime always are connected by a red edge to denote this augmenting path. And then I and j prime is actually connected by a blue edge, if ui and the vj prime actually connected by at least one blue edge. Okay. So for example, in this example, the supergraph representation is actually just simplify the following. So we have this like a solid red edge here, 1 and 1 prime, actually denote this long augmenting path through this U1 to V1 prime. Okay. And now this blue edge is just the long blue edge between U1 and the V2 prime. And now after this simplification, now our job is just to look for alternating cycles in this supergraph. So in particular, each alternating cycle in this supergraph can be expanded into the alternating cycle in the original graph. And also, we will show that later, the supergraph actually can be made as a very supercritical, like Erdős random graph with a planted perfect matching. So here, very supercritical just means that the average degree is actually much bigger than 1. And then because of this supercriticality, we can further show this supergraph actually indeed contains exponentially many alternating cycles of length linear in N. Okay, and that basically completes the proof. Now, after we found this, then we can expand this to the alternating cycle in the original graph, and then we get what we need at the beginning. Okay, but then there's something that I haven't told you is actually how I actually constructed the path in the first stage, right? So let me actually mention that. So for the general distribution, we actually do that using this neighborhood exploration process to construct this so-called two-sided tree. So basically, you focus on a particular red edge, let's say ik and ik prime. You start from ik, do the local exploration, and to construct this left tree. Okay, and now you start from ik prime and then grow a right tree. And now these leaves on the left subtree actually are called, it's actually my lk that I shown you earlier. And now the leaves on the right of the right subtree is actually the rk. Okay. So that's basically the high level idea. You do this local exploration process and then to construct this two-sided tree. But now here there's a challenge. It's a very subtle but very key challenge here is that there are three things I want to actually have. I want to have a large LK and RK because eventually that will help me to actually connect them using Weiss sprinkling. I also wanted the passes to be augmenting in the sense that the log likelihood weights of the blue edges exceeds the log likelihood weights of the red edges. And then also I want to not use too many vertices in this construction because after finding one such two-sided tree, I'm going to delete that in the graph. And then in the remaining graph, I'm going to extract another two-sided tree and then repeat that, right? So I want to actually be able to extract many such two-sided tree. Ideally, I want to do not use too many vertices in constructing each one of these two-sided tree. Okay, but then if you just do the natural exploration process, unfortunately, you will end up with using too many vertices. So that's why here we come up an idea called exploration and selection. So basically, we now run the exploration process using the breadth first search in different epochs. So each epoch is actually represented by the dashed line here. And each epoch actually has certain steps. And now the crucial thing is that at the end of each epoch, I'm going to actually, the only leaves with augmenting alternating paths to the leaves actually are selected and further grown. So this actually highlights using the black nodes here. Okay, you can see that here, I do not further grow this one because the alternating path to the root is actually is not augmenting. Okay, so now now you can imagine these selected vertices like the blue, the black nodes here actually grow like a branching process with mean offspring is actually given by this expression here. The idea is that if you do these edge steps, you will end up with roughly d to the power of h many leaves. And now each leaf will be selected with a small probability governed by this Barachari coefficient. And remember, actually this factor is actually bigger than 1. So if you choose h to be large, this branching process is actually supercritical. So that's why in the end, we can imagine we will have many actually selected leaves. Okay. So that's basically what we do for the general distribution. But now, okay, we can also follow this rougher procedure under the exponential model. In particular, we can follow this two-stage cycle finding scheme. But unfortunately, this tree-based procedure, like this tree-based path construction procedure, is too wasteful. Okay, the short answer is that you construct a fat tree, but you only actually use one pass in the end to construct the cycle, right? You can see that in this exploration process, I construct this fat tree, but then on the end, I only select one pass. So this is too wasteful. And this somehow suggests that we should actually directly look for alternating paths in this exponential model. So that's exactly what we did here. But we do that in 2 steps. Okay, we first actually try to show there are many short alternating passes using the first and second moment method. But then note that here, these alternating passes may overlap. Okay, we want some disjoint, vertex disjoint alternating passes. So that's why in the second stage, we actually extract a large collection of vertex disjoint passes using the Turan theorem. And I should say that here, the program largely follows the previous work, but the previous work actually considered very different context. So let me actually show you a little bit more about each of the steps. So the first step, under the exponential model, a simplification is that the log likelihood weight is just some scaled and shifted version of the negative of the observed weight, okay? So when an alternating path P is augmenting, just reduce to say that the total weight of the red edges exceeds the total weight of the blue edges in terms of their directly observed edge weights. So somehow this suggests that we can just directly work on the observed edge weights. We don't need to worry about these log likelihood weights in this exponential model. And now to ensure this augmenting path is actually augmenting, we actually separately control the total red and the blue edges. In particular, we actually require the mean weight for the red edges is around this constant about 2 over lambda. And now the mean weight for the blue edges is actually slightly below 2 over lambda. So you may wonder why I have this 2 over lambda here. So this 2 over lambda is actually the value where if I conditional on like the total red weight to be larger than the total blue weight, then actually typically you will see that if I condition that, then the mean weight for the red edges and then the blue edges will be close to 2 over lambda. So that's why I choose this 2 over lambda here. But then it turns out that this is still not enough. We still actually further need to impose this so-called uniformity constraint to reduce the correlation between different alternating passes. So the high-level idea of the uniformity is just to say that, okay, not just for the entire pass, for every subpass, the edge weights, the deviation should not be too large, like should be small. So in particular, we require the deviation of the total red and blue edges in every subpass is actually bounded by 1 over square root of epsilon. And this 1 over square root of epsilon is chosen in this way so that after imposing this uniformity constraint, still I have many alternating passes. And now basically I'm almost done. I can just define or denote the set of alternating passes, satisfying this total weight constraint and also the uniformity constraint. And then I can go ahead and compute the variance and the first moment. I can show that the variance is actually smaller than the mean square times this ratio here. So here, L squared over n is actually roughly the probability if you have two like alternating paths of length L. So that's the probability they overlap. They overlap with probability L squared over n. And this exponential 1 over square root of epsilon is actually the penalty that I need to pay because of the deviation of the weights in this subpass. Okay, so that's what we did. Now we just need to extract like a large collection of the vertex disjoint passes using Turan theorem. So the idea is the following. We can now just define a graph edge where the vertex actually corresponds to these good alternating passes in this set SL. And now two nodes are connected by an edge if the two corresponding alternating passes share at least one common vertex. Okay. And then after this definition, you can convince yourself, if you look at the independent set of edge, this just means that you have this collection of vertex disjoint alternating passes, right? Because independent set just means there's no edge. If there's no edge, that just means that the corresponding alternating passes actually are vertex disjoint. Okay. Now our job is just try to show in this edge, we have a large independent set. So that's where we use this Turan theorem. Basically, Turan theorem just tell you that a lower bound on the largest independent set for any simple graph in terms of number of vertices and in terms of number of edges. Okay, and now we just need to apply this Turan theorem into our context. The number of vertices actually happen to be roughly the same as the expected value of the cardinality of SL. And now the number of edges is just corresponds to the variance of this SL, because the variance will matter in terms of the overlap. And that's why the number of edges here also depends on the variance. And now I just need to recall my variance bound. And now I can quickly show that there exist this many vertex disjoint alternating passes of length L. And now in the end, I'm just optimally choose my L in this way. And I can get the desired augmenting alternating cycles by sprinkling. And the length is actually given by this n times exponential of -1 over square root of epsilon. And if you remember, that's exactly the optimal error rate bound that we have. And you see this exponent 1 over square root of epsilon actually come from this uniformity constraint. Okay. So that's all I want to actually say about the analysis. Now, actually, let me use the remaining time to actually conclude my talk and mention some open questions. So in this talk, I actually show you actually this sharp threshold for almost perfect recovery where the reconstruction error is vanishing. And this is actually determined by square root of average degree times the bipartite coefficient equals 1. And then also we see an infinite order phase transition under the exponential model. In particular, we see the optimal error is actually exponential with -1 over square root of epsilon up to some constant when lambda is slightly below the threshold. And the key idea of our proof is actually this two-stage cycle finding procedure. We first actually construct passes, and then we connect them using sprinkling. And also under the exponential model, a crucial thing to get this tight optimal error bound is to further impose this uniformity constraint. So there are actually a number of very interesting open problems that are not just by our work. The first one is that we look at this optimal error bound under the exponential distribution, but then what about the general distributions? And also we only be able to determine the optimal error bound near the threshold, like at this criticality. But then how about the entire parameter range? How does the optimal error depends on the model parameter? And also there's a natural extension to this model called Planck K-factor model. So K-factor here just means that it's actually a spanning K regular graph. Like every vertex has a K like incident edges. So there's a very natural conjecture extension actually to this model made by recently by one of the previous work. So it's given by this threshold here. So the positive part of this conjecture is actually relatively easy to prove using our analysis of max and likelihood estimator. But the challenging part is actually the negative part. So we're not sure, for example, how to extend this our two-stage cycles funding procedure to show the negative part of this conjecture in this K-factor model. And also I should mention that at the beginning, as I said, there are many different plant models driven by many different applications. So you may actually encounter some other planting models, for example, spanning trees, traveling salespeople, depending on the application they're looking at. So it'll be also very interesting to study those applications. And also one thing I should also mention is that even in this particle tracking application, the model that we're considering here does not consider the spatial kind of information. So you might also want to consider more realistic spatial model for particle tracking problem. I think that's all I want to say. And here is actually the reference for this talk in case you want to understand, to take a look at the more details. I'm happy to answer any question that you have, and that's all. Thanks.
Let's thank Jiaming.
Thanks.
Okay, if you have any questions, feel free to unmute yourself and ask.
Yeah, I think David has a question.
Go ahead.
Yeah, sure. Can you hear me?
Yeah.
Yes.
Okay, so a few like just high level questions. So one high level question, like, so once you've done the factor of two observation and kind of reduced it to a question about two coupled samples, or that's how it intuitively seemed, I'm a little confused at a very high level about why you need the quite elegant and sophisticated lower bound on the posterior mass versus just saying like, look, I have two coupled samples in expectation, they don't overlap enough. And I can convince you that the number of edges that are bad is linear in expectation, which would seem to be like a much simpler argument. I don't intuitively grasp why something simple like that doesn't work once you've reduced it to a question about these two coupled samples. Does that make sense? Why that would be?
Yes.
Do that?
Yeah, so I think I understand your question. So yeah, you're right in the sense that the M star can be viewed as a sample from the posterior distribution. Like the true matching is a sample from the posterior distribution. M tilde is another draw from the posterior distribution. So indeed, the problem reduced to actually study the expected overlap between these two independent draws from the posterior distribution. But I think the question here is that, yeah, this is exactly what we want to do, but how to actually bound this expected overlap is still not that trivial. So I don't see in particular, for example, like how you can do that, even if you reduce that to compute the expected overlap between two independent jaws. So in fact, that's basically what we're trying to do is actually try to bound the expected overlap. So let me actually mention about this plot, which maybe will help. So basically like M star is the one posterior jaw, you can view in that way. And you have another jaw, right? You somehow want to show M tilde will be far away from M star. So a very natural way is just try to bound the total probability mass that is near M star, and then try to lower bound the posterior mass that are far away. If you can show there are more posterior mass here, then if you draw another one, then very likely that will be far away from M star. So that's basically the high level idea.
Okay, it would seem like you just need this much simpler quantity of like the expected number of edges that are like, you know, in that, in one and not the other, but I can do that. So, okay, no, that's, so another high level question that when I put the paper out, I was really struck by this, the factor of two thing, and two questions there. So point one, is that like has that idea been used before? Was that, that seems like quite an interesting. But it's a follow-up question. So then the second part of that question, which is related to the first part, is like, is the intuition that for most problems you think this inequality actually gives roughly how it should behave, or is there something special going on here where that kind of simple reasoning actually seems to yield a tight analysis? Okay, yeah. So let me first answer your first question. So I believe this observation is indeed like a focal law for people who study, who are familiar with this Bayesian inference. So indeed, I tried to Google it, and I couldn't seem to exactly find a use of that anywhere else. Is there a paper where that was, because it seems like a really cool idea, you know? Okay, yeah, that's actually a very good question. We don't find a very precise reference for this observation. It's more like a focal law for people who are in this. Yeah, so I mean, this is indeed some very simple but very useful observation. I think maybe some of the reason is that for people who work in these quantity models, I mean, so sometimes they don't really need to actually study this posterior distribution this precisely to get the Sharpe threshold. For some other problem, you can, for example, directly analyze max likelihood estimation. Here we want to do this because of this particular problem. But then to your second point is that about this factor two, right? I think one thing I can say that the optimal estimator in minimizing this reconstruction error is actually not the posterior sample. It's actually this so-called marginal maximum posterior. So basically you compute for every edge, you can compute what's the probability of this particular edge in the hidden matching. Yeah, no, and then you just and then you just truncate that posterior probability at 1/2. That will give you actually the optimal estimator. But I guess it seems quite interesting that asymptotically this seems to give all the right answers. And so, do you think that is that kind of known to hold broadly, or is this exception? I see. So I don't want to claim like this, nobody knows that, but indeed, when I first study this problem, I actually didn't realize this at the beginning. So it actually took us a very long time to actually realize this observation. So in fact, actually, at the beginning, we actually look at some very different routes where we try to come up some fake matching. Yeah. So yeah, I want to say, probably this is very useful, but not everybody actually know this. And then final thing, and then I'll keep my mouth closed. So maybe it was implicit in one of your proofs, or maybe I missed it. So is like local reconstruction using some kind of belief propagation thing, or just some kind of, like what had been done, planted clique by, Montanari and Deshpande or whatnot. Is that implicit in your work here, or do you think is this an inherently global kind of analysis? Right. Actually, that's a very good question. So I don't have time to go into that. So here we studied this okay. So indeed, if you want to actually study the optimal reconstruction error in this entire parameter range, then you should actually try to study the belief propagation algorithm.
So yeah, in particular, you can use the Belief propagation algorithm to approximate this marginal like probability, posterior probability, as I said before, and then that will possibly give you the optimal reconstruction error. But that object is actually very difficult to study in this setting. So we actually don't know actually how to rigorously study this. But one thing that we do know how to study is actually based on this local weight convergence theory, is that if we instead of looking for Belief propagation, like there's two versions, we call it sum product and then the maximum product. If you do maximum product, that will correspond to MLE, the maximum likelihood estimator. So we can indeed actually use the local weight convergence theory to study this maximum product Belief propagation. And in particular, that's how actually in the earlier work, we actually come up with this exact overlap of MLE.
Okay.
So this is actually through this local weight convergence theory to study the Belief propagation to some extent.
So your work, it does imply that a local type iteration can recover the optimal structure when it is recoverable. That's
yes, I think so.
okay.
Yeah.
Cool. That's it. Thanks.
Jiaming, Rajesh here. Can I ask a question?
Oh, yes, sure.
I would like to see your theorem number 1, which was there in the beginning.
Here, right.
Yeah. So here I see that if you fix the DPQ, then if root D and the Bhattacharya distance is less than or equal to 1, it goes to 0. And if it is larger than 1 plus epsilon, you have a positive constant. So I'm wondering if we write this constant as a function of the Bhattacharya distance and look at it as the Bhattacharya distance increases from below 1 over root D to above 1 over root D and goes beyond. How does the C as a function of this distance vary? Do you have any idea? And is that related to your infinite order phase transition? Is it a smooth transition? Is there something that can connect to the?
Yeah, so indeed, I think, okay, so if I understand you correctly, indeed, here the constant C depends on epsilon. And then in fact, it can also potentially depend on DPQ here. Okay, so indeed, like if you look at this, say square root of D times Bhattacharya coefficient, let's say equal to 1 plus epsilon. And then if you let epsilon go to 0, so you want to study how C epsilon behaves. And that's indeed related to this order of phase transition that we've talked about. So in the exponential model, we can actually precisely get the C epsilon actually decays to 0 as e to the minus 1 over square root of epsilon, roughly. But for the general distribution, we actually do not know. Okay, I think that's one part. And then the other part, I'm not sure if you worry about the other part is that if the square root of D times BPQ actually be very large. Okay, so in fact, then we're in the very worst situation. In that case, you can, using the monotonicity, you can reduce that to just set this to be 1 plus epsilon. You can still get this, the result here. But I'm not sure whether you're worried about that part.
Thank you.
Yeah.
So Jiaming, do you have any comments on how the results would look like if the goal is to get a like a high probability recovery of M star?
Oh, right, yeah. So in this talk, I didn't talk about this so-called exact recovery, where your goal is to say M star, like M hat, the estimator exactly equals M star with high probability. So that one actually is much simpler to study. In fact, one thing that we know is that when this quantity goes to 0, so the square root of D times Bhattacharya coefficient goes to 0, then you will know that M hat of maximum likelihood estimator will be equal to M star with high probability. I believe you can also study the maximum likelihood estimator to get a converse result, because in that setting, the maximum likelihood estimator is actually optimal because the prior of M star is uniform. So you can just study the maximum likelihood estimator to get a matching converse result. So yeah, that one, I think the major difference is that one is slightly simpler to study than the scenario that we consider here.
I see. Okay, yeah, great.
Yeah, thanks.
Okay, let's thank Jiaming again and end the seminar today.
Okay, thanks.
I mean.
Okay, then bye.